Welcome to MathGPT. Today, we'll explore the fascinating connection between the standard model of particle physics and the emergence of complexity in our universe. How is it that the simplest building blocks of matter can give rise to the incredible complexity we see around us, from stars and planets to living organisms and even human technology? Let's start at the most fundamental level, the standard model of particle physics. The standard model describes the basic building blocks of matter and the forces that govern them. It consists of 12 fermions, 6 quarks, and 6 leptons, which are the matter particles, along with 5 bosons, which are the force carriers. These particles and their interactions are completely described by a set of fundamental parameters in the standard model Lagrangian, including coupling constants like G sub s, G, and G prime, Yukawa matrices Y sub f, and Higgs potential parameters mu squared and lambda. Moving up a level in complexity, we encounter the phenomenon of confinement, where quarks combine to form hadrons like protons and neutrons. Due to the strong nuclear force described by quantum chromodynamics, or QCD, quarks cannot exist as free particles. Instead, they are bound together by gluons, the force carriers of the strong interaction. The QCD Lagrangian contains terms like G sub mu, nu G to the mu nu, with coupling constant G sub s, which leads to this confinement. Remarkably, about 99% of the mass of protons and neutrons doesn't come from the masses of the constituent quarks, but from the binding energy of QCD. This is our first example of emergence. The mass scale lambda sub QCD, approximately 200 MeV, emerges from the dynamics of the theory, not directly from the parameters. At the next level, protons and neutrons combine to form atomic nuclei. The residual strong force, which is a secondary effect of the QCD interaction, binds these nucleons together. This is like a leak of the strong force outside the protons and neutrons, mediated by the exchange of composite particles called mesons. This binding creates a variety of stable elements, from hydrogen to uranium, with different binding energies per nucleon. The curve of binding energy explains why certain elements are stable while others undergo radioactive decay. This nuclear binding also allows for isotopes, variants of elements with the same number of protons but different numbers of neutrons, creating another dimension of variety in the periodic table of elements. Moving to our fourth level of complexity, we add electrons to our nuclei to form complete atoms. This is where the electromagnetic force, mediated by photons, becomes the dominant interaction. The electromagnetic interaction is described by terms like F sub mu nu F to the mu nu in the standard model with coupling constant E, which is related to the couplings G and G prime. Electrons, being much lighter than the nucleus, form orbitals around it based on solutions to the Schrödinger or Dirac equation with the Coulomb potential. These electron shells give atoms their chemical properties. The arrangement of electron shells leads to the periodic table of elements, where elements in the same column have similar chemical properties because they have the same number of electrons in their outermost shell. When atoms share or exchange electrons, they form chemical bonds, creating molecules with completely new properties. This is our next emergent phenomenon, molecular structures and chemical reactions that arise from the underlying quantum mechanics of electron interactions. At the fifth level, many atoms and molecules come together to form condensed matter, solids, liquids, gases, and more exotic phases like superconductors and magnets. These different phases of matter emerge from the collective behavior of many particles. The same atoms can form different phases depending on temperature and pressure, with dramatic changes in properties at phase transitions. A key concept here is spontaneous symmetry breaking, where the system spontaneously chooses a state that is less symmetry than the underlying physical laws. This is the same mathematical phenomenon that occurs in the standard model with the Higgs mechanism. In condensed matter, we get collective excitations like phonons, sound waves, magnons, spin waves, and many others. These act like effective particles in the material, even though they're really collective motions of many atoms. Finally, we reach the sixth level, the complexity of living systems. Chemical networks under energy flow can self-organize into complex structures far from equilibrium, such as metabolic cycles and cellular membranes. Information-rich macromolecules like DNA store the genetic code, which can be replicated and passed on to future generations. The specificity of DNA-based pairing relies on the quantum chemical properties of atoms we discussed earlier. Living systems exhibit an astonishing hierarchy of organization, from cells to tissues to organs to organisms to ecosystems. Each level has emergent properties not obvious from the level below. And, remarkably, all of this complexity, from the simplest living cell to human consciousness, ultimately emerges from the fundamental particles and interactions described by the Standard Model. In conclusion, we've seen how complexity emerges in layers, from the Standard Model's fundamental particles to the nuclear physics of hadrons to atoms and chemistry to condensed matter phases, and finally to living systems. Each layer exhibits emergent phenomena that aren't obvious from the layer below. Scale separation allows each layer to have its own effective laws, largely insensitive to many microscopic details. It's also worth noting that the Standard Model parameters must be finely tuned to allow for this richness of structure. Small changes in the strong interaction scale, the electron mass, or the proton-neutron mass difference would prevent complex chemistry and life from emerging. In the grand scheme of physics, emergence is a unifying concept that connects the simplest fundamental particles to the most complex systems we observe in the universe. The Standard Model may be the foundation, but the emergent layers built upon it are what give us the rich, complex world we experience.